Hi everyone, and welcome to the Silently Breaking ASLR in the Cloud briefing. This is joint work with Mathias from Purdue University and Thomas Groß from ETH Zurich. I'm Antonio. I'm co-founder of a Swiss-based IT security company called Zorlab. And this here next to me is Kaveh. He's a security researcher in the system security group here at VU University Amsterdam. The outline of the briefing looks as follows. So we'll first talk a little bit about the threat scenario. Better. So we will first talk a little bit about the threat scenario, so actually the starting point of the attack and what we assume the attacker already has. We'll then look into memory deduplication, the root of all evil in that case that makes the attack possible, and then at the side channel that we're going to exploit. Then we present the attack called CAIN, Cross-VM Address-Based Layout Randomization. We'll show you some evaluation results of the proof of concept that we implemented. And then we talk a little bit about what an attacker actually can do after he used CAIN and look at some mitigations. So what we assume is the following scenario. We have a physical hardware with a virtual machine monitor on top of it and 2 or more virtual machines running on that. We further assume that there is an attacker already on one of these systems. So there is one attacker VM where the attacker is either in control of that VM or has just user privileges. The attacker wants to attack a neighboring victim virtual machine, and he knows a memory corruption vulnerability in a process that runs on that VM. So usually what happens is the attacker has a memory corruption vulnerability and he will try to hijack control flow. And to mount a code reuse attack, he will need to know the addresses of libraries or code locations. Now, nowadays, that's not that easy because there is address-based layout randomization in most modern systems. So the code locations are randomized in memory. Now, what we will show today is the following. If the virtual machine monitor has same content page-based memory deduplication enabled, then it is actually possible for the attacker to infer the base addresses that are randomized of codes of libraries and executables that are mapped in processes of neighboring virtual machines. Thus, the attacker can use that base address that he leaked and construct the code reuse attack. So we present cross-VM address-based layout introspection. And it's a new attack vector against memory deduplication. It's tracked under that CV, so 2015-2877. There's also a vulnerability note from cert.org with some additional information. And it makes it possible to leak the randomized base addresses of libraries and executables, of processes that run in other VMs. Now let's look at memory deduplication. Now, there are virtual machine monitors that use this memory deduplication. I mean, there is KVM, VMware has it implemented, VirtualBox. And what actually happens is the following. So there are 2 VMs, and the color of these pages are the contents. Now, when 2 pages have the same content through over 2 VMs, the memory deduplication scheme tries to find these pages. It will scan for these pages, and as soon as it found 2 pages with the same content, it will merge them to one physical page. Now, as soon as one of the VMs, now in that case VM A, writes to that page, there will be a copy on write operation. So the page will be duplicated again from physical memory, such that the VM A can easily write to it and everything is fine again. Now, the problem with that is that there is a security pitfall here. Namely, if VM A observes or measures the write times to that page, it will measure a significantly higher write time to the shared page compared to other pages. And this opens up a side channel that the attacker can exploit. Now, from the attacker's point of view, it looks like this. So the attacker is in the attacker VM, and there is this side channel, and then there is memory in the victim VM. So these are all pages, and there is this blue page. What the attacker can do is the attacker can guess that page, so he has to construct that page in his memory. And then the attacker just waits for a certain amount of time till the memory deduplication scheme finds these 2 pages and merges them. And then the attacker just writes to it. And if that write time is bigger than a certain threshold, the attacker can deduce that this page existed in another VM. And if it's not the case, then he can assume that this is not the case. So, and this is the side channel that we're going to use to break ASLR of co-located VMs. Now, from the attacker's point of view, we have several challenges that we have to solve. So the first challenge is actually what should the page contents be of that page? So the attacker has to construct guesses. Second, the attacker has to wait for a certain amount of time. So the attacker has actually no idea about how long he has to wait till these pages get merged. And then third, the attacker has to write to it, measure the time, and then deduce or infer if that measured time might indicate that the page was merged or not. So there is noise in that channel because there are also write times that are higher because of, not just because of memory deduplication. And the question is also what kind of threshold should be used. And finally, if these challenges are solved, the write time will reveal if that page was shared. The attack looks as follows on the high level, and we will look at all of these phases in more detail. So we have a first phase that we call the adaptive sleep time detection phase. Then there will be a round of filtering. You'll understand later what I mean with a round. And then there will be the verification phase. And at the end, what comes out is the base address of a library in a co-located VM. Now let's look at the first challenge, the page contents. Now, when we were thinking about the attack, we were looking for certain kinds of pages, of course. And these pages have certain criteria, or they have to follow certain criteria. So one of it is the pages have to be page aligned. And the reason for that is we'll have to construct pages where the memory deduplication scheme scans through the pages, and it always starts at offset 0. So it tries to detect if these pages are the same or not. So we need ideally page aligned pages. Next, the page has to be mostly static because it takes some time till these pages are actually found. So if the page changes in the victim VM's memory, then this sharing will just not happen. So ideally it's read only in the victim VM, and we need to know that it exists. So it needs to tell us something about the address space layout or about the randomized base address. So ideally, we have all these criteria met, plus this page should contain the randomized base address of an executable image. So that's the best case. Or what would also work is if that page has values that are based or are derived directly from the base address. So the overall idea is actually to identify pages that we can somehow construct and that have the entropy of the address space layout randomization scheme. So the attacker should be able to construct such a page except for the entropy bits of ASLR. And in that case, for a DLL in Windows, for example, 64-bit, it would have been 19 bits of entropy. Now, when we find these pages, and if we can show that this page exists in a co-located VM, we can actually infer the randomized base address. And this is what we were looking for. So it looks like that it's maybe difficult to find in the beginning, but it was quite interesting. So when we were looking at these pages, when we were trying to identify them, we'll actually, if you look at the first page of every executable image, so a DLL or an executable in Windows, on disk it looks like here on the left. So we have a portable executable file that has header information, and there is a very interesting field called the image base field that has just a certain value on disk. But as soon as these portable executable file gets mapped into memory, so this happens with DLLs and executables, the image base field will be adapted. And it will then contain the runtime randomized base address of that DLL or executable. So this first page of every portable executable image actually fulfills our criteria. So we were very lucky here, so we just found it by looking at the first page. And so we can reconstruct that page except for these bits of entropy for the randomized base address. Now, we also found these pages on 64-bit Linux. It's a bit more complicated there. It's not that apparent, but if you're interested in just come to us later and talk to us or write us an email. Okay, so still one problem remains. So the attacker still has to actually guess that correct value. And the problem, of course, is we have 19 bits of entropy. So there are 2 to the power of 19 potential base addresses for a DLL in 64-bit Windows, which in the end are more than 500,000 guesses that the attacker would actually have to guess. So one guess requires one page at a time, and if the attacker will do that one after each other, well, the attack is not that feasible then. But there is a very common offensive security concept, right? So if it doesn't work, you're probably just not using enough. So the idea here is to actually use all the memory that an attacker VM has to do that simultaneously. So in the end, we implemented a brute force attack on these pages. So the attacker VM uses all the memory that he has by guessing all the potential base addresses at once. And in the case of 64-bit Windows, that's not a problem because there are 2 to the power of 19 guesses times one page, which is 2 gigabytes of memory. So if the attacker VM has 2 gigabytes of memory, the attacker can do that in one go. So the attack presented in the end is a brute force address over that memory deduplication side channel. So we allocate all these first pages of DLLs, for example, for a particular DLL. We put all the guesses in there for the specific base address. And then we just try to detect it. And at the end, you'll find the right base address by detecting which one of these was actually shared or not. So we solved the challenge of the page contents. Now the question is, of course, how long should the attacker or the exploit wait? Now, this depends, of course, on the memory deduplication scheme and also on the memory deduplication configuration. So the memory deduplication implementation will work differently on different implementations. So we didn't want to actually assume a certain implementation. So this also varies in the end on the amount of memory that is actually used. So if you have like 2 VMs with 2 gigabytes each and compared to 4 VM with 2 gigabytes each, it takes, of course, more time till the memory deduplication scheme was able to compare all these pages to each other. And in the end, as an attacker, we have to assume the worst case. So we have to assume that the page or that we guess, that we construct, will be maybe compared to the right page right at the end. So depending on how much memory is used, this might take longer. So there is also an attacker trade-off here, of course. So if the attacker waits too little, the attack will just not work because the page will not be, the guess will not be merged. And if the attacker waits for too long, then the overall attack time will increase. So there is this trade-off that the attacker has to balance. And what we tried, or what we implemented in our proof of concept is an adaptive sleep time detection algorithm. So what we do is we basically create a random buffer of a lot of pages. We then copy every second page of the first half of the buffer to the second half of the buffer. So this creates the following situation as we see it on the right. So there are now a lot of pages that are pairwise equal, so they have the same content. So we create a lot of potential merging opportunities for the memory deduplication scheme. And then we just wait a certain amount of time. So it's adaptive, so we wait, for example, 10 minutes. And then as soon as these 10 minutes are gone, we start writing to all these pages and we try to detect which of these pages might potentially be merged. And then we get a detection rate. And depending on that detection rate, we either rerun that again with a higher test time, or we take that test time and say that's a good estimate for the sleep time. So actually, more specifically, what we do is if the detection rate is more than 95%, we just return the last tested wait time times 1.2 just to have some additional margin. And if the detection rate is less than 50%, we double it. And if it's something in between, we multiply it by 1 over the detection rate. So it gives us better estimates for the next test time to test. And only if it's over 95%, we actually return that test time and use that in the next phases of the attack. So we found now the page contents that are interesting for us to break ASLR. We know now how long the attacker has to wait for the memory deduplication scheme to find these merging opportunities. So the next thing is, well, how do we actually detect if one of the pages is merged or was merged or not? And what we do is always the following. So we have 3 pages that we allocate adjacent to each other, and we always assume that we are going to try to detect if the page in the middle is shared or not. So we can assume, because we can construct that buffer, that the first page and the third page are actually not shared by putting some random values in it. We then wait the wait time that we detected, and then we start to write to this page. So you write to the first byte of the first page, the first byte of the second page, and to the first byte of the third page. And then we measure write time. And depending on these values, we can then actually deduce if that page might have been potentially merged or not. And for that, we use a set of heuristics. So one heuristic the first one on the left has to be the case all the time. So we check for that all the time. So write time of T2 has to be at least 2 times the average of the adjacent write times. So it took us some time to find out what kind of threshold is good. So we went for a rather conservative approach. So we took 2 as the threshold factor here. Everything else might generate some false negatives. So that's why we took 2. And then we end that with either the second condition, so T1 and T3 have to be less than 1,000 cycles, or the T1 and T3 should not diverge too much from each other. And this was just by observing a lot of runs, we were just able to see that usually T1 and T3 start to diverge from each other very quickly when noise happens. So in the end, these are just heuristics. We use them, and they worked, for example, on a laptop setup and on a server setup where we evaluated our POC that we will show you later. So it seems that these heuristics work quite well, but of course an attacker can invest also more time to implement better heuristics. Okay, still one of the problems is there might be false positives. And if a false positive actually happens, we'll just test it again. So we have a round-based system that I will show you right now. And there might also be false negatives, and in that case, it's not that critical. So that didn't happen that often. But if it happens, the attacker can just rerun the attack. So now for the false positives, of course, we don't want to have them. So the idea here is to do multiple rounds till the noise cancels out. So what we do is we allocate these guesses. So in that case, guess 1 till guess n. And then we try to detect them. And in the set that comes out, we'll have some false positives and the correct guesses. And we just take these again and do it another time. Now we have 1 false positive. And in the end, we find the right solution. And we can actually do that and assume that that works because the probability that the exact same guess will be affected by noise 2 times or 3 times after each other is quite low. So noise happens it doesn't affect specific guesses, it just happens randomly. And through that we can eliminate the noise. Now what we implemented is actually we have 2 types of rounds. So the first round is a little bit different than all the subsequent rounds. In the first round what we do is we have implemented a so-called filtering round. So in the beginning, if you have a lot of guesses, the problem is that it will take a lot of memory. So assuming that the attacker has maybe just 2 gigabytes of memory, what we do in the first round, that is called the filtering round, we allocate all the guesses adjacent to each other. So we just assume that the probability that 2 adjacent base addresses are used in a co-located VM is low. And then we try to detect it with this moving 3 windows test. And then for every other round, we actually can assume that we have more memory. So we can invest as an attacker more memory per candidate. And in that case, we allocate random pages in between. This makes the attack just more reliable. But we have to pay with memory for it. Okay.
Thank you. So does it work? I mean, the idea of the attack makes sense, but there are lots of things that we had to take care of, like noise, there are false positives, false negatives. So we're asking ourselves the question of, does it actually work? So, and to actually answer that, we went on and implemented the proof of concept that we called CAIN, and we evaluated the attack using CAIN to see whether it actually works and how well it works in practice. So remember that there are a number of requirements that we assume for CAIN to work. The first one is that the side channel actually exists, so that we have a memory deduplication engine running all the time. And this happens to be the case in most cloud providers that we looked at, especially the ones that run, for example, KVM. And the other assumption is that we have a page that we can actually use for breaking the address space layout randomization. Antonio showed you that we managed to find these pages for Windows and Linux operating systems. You can also use other pages for leaking information, like, for example, antivirus versions or fingerprinting operating systems, for example. But the interesting bit here is address space layout randomization, which we try to break. And also the final assumption is that the entropy that we are trying to leak here is within brute forceable range. So for example, given an amount of memory that the attacker has, for example, 4 GB, we can actually brute force all these bits that we want to leak. So just briefly, let's go over the CAIN attack phases again. So in the first phase of the attack, we actually try to figure out how much we need to wait in each round of the attack for pages to get merged. And this can be like, depending on the configuration, this can be anything. So we have an adaptive algorithm that tries to figure out what time we need to wait. And then in the second round, we do a filtering pass where we have a huge number of pages, like 500,000 pages. If, for example, we have 19 bits of entropy. And our goal here is to reduce the number of cases that we need to check further. In this case, we might have some false negatives, but that's fine. We can always run the attack again. But in our experience, that didn't happen that often. And finally, in the last phase of the attack, we do verifications of the candidates that we have found. So we keep doing that. We keep repeating that verification pass till we manage to reduce the set of the attacks either to 1 or when it doesn't change. And this could take up to n rounds. And after that, we have the address space layout of the neighboring VMs. So for the evaluation setup, we use the Blade server. So this is what you can typically find if you go to any data center. This is usually like you find like a rack of these servers, and they're running your VMs. And this server specifically has 2 CPUs, and it has 32 GB of RAM, so very common in cloud data centers today. And we use a recent version of Ubuntu and KVM for evaluating the attack. So for the VMs itself, we used one attacker VM that we control, and then we assume up to 6 other victim VMs that we try to attack. And for the configuration of these VMs, we used 4 cores and 4 GB of memory. So just to give you an idea of how the memory deduplication on KVM works, I briefly now discuss its deduplication engine that is called KSM. So you have a number of files in those locations that you can control the configuration of the memory deduplication. So the first one tells you whether the deduplication engine is on or not. So if you have a Linux system, most of the times it's actually on. And there are 2 other parameters that affect how fast your pages get deduplicated. So the way KSM works is that it goes to sleep for a while, then it comes online, and then it checks for a number of pages. Then it goes back to sleep, and it keeps doing that till it managed, and it keeps doing it over and over the registered memory to find duplicates. And and these 2 parameters, like the amount of time it goes to sleep and the number of pages that it scans, decides how many pages are scanned per second. So if you do the math, you can actually find out that it's about 500 pages per second, about 2 megabytes, and this should already give you an idea of how, depending on the amount of memory that you have, how much you need to wait for the pages to get merged. For our target VM, we are attacking a 64-bit Windows Windows Server Edition, and these new recent versions of Windows enjoy from high entropy ASLR for stack and heap, and for executables and DLLs there are like 19 and 17 bits of entropy that you have in the address of in the base address of these executables or DLLs. Now these addresses, this layout is defined at boot time. So once we have managed to leak that, you can actually do the code reuse attack on any of the systems that use these DLLs. So there are some DLLs like anti-DLL that also don't relocate. So once you have managed to leak that address, it's going to remain the same like that. And these are the actual, the anti-DLL is the actual target that we are attacking in the evaluation of CAIN. Now, so for our first attack here, we have one victim VM and we have one attacker VM. You can notice that on the y-axis we have the entropy bits. So in the beginning it's 19 bits. It's for the anti-DLL. And on the x-axis you can see the attack time as it progresses through time. As we mentioned earlier, there are about 500,000 of potential addresses. And once we started the attack, CAIN went through detecting the amount of time that it needs to sleep. This is the default configuration. So we noticed that with one attacker and one victim, we need to wait about 96 minutes for the pages to get merged. And you can notice that after the first round of attack, we managed to already reduce the number of candidate pages from 500,000 to only 6,000, about 6,500. And this significantly reduces the entropy. And after the second round of the attack, we managed to reduce the candidates to about 5. And finally, in the last round of the attack, we have only a single candidate that is actually the address space layout of the neighboring VM. You can note that the entire attack time took less than 5 hours. So if, for example, now you have a VM that is using KVM in the cloud, and you have another one, essentially you can leak its address space layout in less than 5 hours. The first thing that came into our mind for defending against this attack was whether by increasing the actual sleep time we can actually fix the issue. So we did an experiment just to verify that, and the result is that if you increase the sleeping time, it doesn't actually solve the attack. It will make the attack take longer, but it still doesn't solve the issue. So just changing the sleep time doesn't completely solve the issue. Also note that if you increase it too much, then you are completely losing the benefits of memory deduplication. So the idea is that you can actually merge pages that are similar during the runtime of your VMs. So you might come back and tell us that this is a lab environment test. This actually doesn't work in real world where you have lots of noise and lots of requests coming to your VMs. So we did another experiment to actually verify that. So here you can see an example of a web server that is serving a number of requests. So we changed the number of requests that is sent to this server. So the first version, we sent only one request. So that exemplifies a very simple, light loaded server. The other one, 10 requests per second, which is like an average loaded server. And then in the last one, a maximum number of requests per second is that would signify a very heavily loaded server. And you can see that in all these cases, CAIN can leak the address space layout, and it doesn't really matter how much load we put on the server. So finally, we executed the CAIN attack against multiple VMs. And we saw whether it can actually leak all these address space layouts of all these VMs. So I specifically like this graph because it shows a number of things. So the first thing that you can notice of all these different configuration that goes from one victim VM to 6 victim VM with different colors, the first dot starts to change depending on the number of victim VMs that you have. This shows our adaptive sleep time detection in action. So depending on the amount of memory that is registered, it changes the amount of time that we need to sleep, and we can successfully and dynamically detect this. And at the end, we also, depending on the number of candidates, since we are not sure whether it's a false positive or whether it's actually a layout that we have discovered, we need to wait. We need to do another second pass to verify that this set of candidates doesn't change. So after doing these two passes, we successfully could detect all the layouts of the victim VMs. Okay, now that you've seen how CAIN actually works, we're going to show you a demo of CAIN in action. So now I pass over to Antonio.
Thanks. So we prepared a little video demo. So in that case, what we're going to look at is we're going to look at the single attacker, single victim scenario. Just start it. So what you see now is actually the hypervisor or the virtual machine monitor system. It's an Ubuntu Linux system. And on top, we just show you some parameters. So the KVM is running with KSM enabled. So that's why run is 1. That's the default configuration. What we change is the sleep milliseconds configuration. We put it to 20 milliseconds, so we don't have to wait 5 hours. So the attack will just take longer, but it works. Now we're going to start the VM. So here on the right, we'll see the victim VM. This is the Windows server. And on the left, then the attacker VM. We use the Linux system, also an Ubuntu system. Yes, and the attacker actually just needs user privileges. I mean, could also be just the attacker just needs to be able to access the system in the sense that he can execute a binary, or maybe even something else. So ideally, he needs to be in control of memory or memory allocations. So don't get irritated. So the first version of the attack was called VMAP. That's why the tool is called VMAP. We implemented certain switches to actually play a little bit around with it. So we were able to explicitly put the stay time, the wait time there, for example, just to test around. So we logged in now on the victim system, and KSM is already running now. So KSM is already trying to find pages that are equal and tries to merge them. So what we're going to do now, we're going to start the attack. So the first phase is the sleep time detection. So we tested with 10 minutes. We know that 10 minutes is actually suitable here. But in another setting, sleep time detection might take several rounds till it actually found the right time. And now it's running. So we allocated a lot of pages, and now we just wait. So we just have to wait till these 10 minutes pass. So, but of course, so don't worry, we'll fast forward. So, so sleep time detection is after 10 minutes. What happens is the following. So we start writing to these pages and try to detect the rate of merged pages. So as you see, we already were able to see that more than 99% of the pages got merged. So we then just take these 10 minutes and say 12 minutes is a good estimate for the wait time. So next we start with the first round of attack, so the filtering round, where we allocate or where we map this first NTDLL page and adapt all the base addresses. And after these 12 minutes, so we'll see that we were already able to reduce the number of candidates to 1,165 candidates from more than 500,000. So now entropy is reduced significantly, of course. So the attacker could also already use these values if he has multiple try for the exploit, for example. Now we verify them. So we do another 12 minutes round. And after these 12 minutes, what we see is that the attack succeeded. So there is one last hit. That's this base address. So this should be the base address of NTDLL in this VM, in the victim VM. So it's 7FBE59F0000. So we're going to verify this by looking at the running process. It somehow feels like a card magic trick. So choose a card and we show you which one it is. So here is the NTDLL, and on the left you see the address, which is 7FBE59F0000. So the attack was successful, and we were able to leak the base address of NTDLL over VMs. Okay. So the question now, of course, is, what does the attacker really gain? It's not like a remote code execution attack, so we are not able to execute code, right? So the attacker still needs something, and it's important to understand for the impact of that issue. So what an attacker essentially gains is he can de-randomize the code layout by getting these base addresses, and if he knows this memory corruption vulnerability, he can construct an exploit that previously might not have been possible to exploit. So against one single victim VM, it's quite easy, right? So you have one base address and then you can just use it. But of course, if multiple victim VMs run with the exact same Windows version, for example, you just get a list of base addresses of NTDLL. And then, of course, there might be the possibility that the attacker can just try all of them. So it depends if the vulnerable process gets restarted, and then it will work. we argue that most probably the number of tries that you need is still below a certain threshold, so that it should not be too noisy, so the process should not crash too often. But of course, this might not be possible for certain attacks. So what we thought a little bit about what an attacker could do in these cases. So we have certain ideas. So if you're interested, you can also come and talk to us. So the idea in the end is there are also opportunities or possibilities to map this base address to a specific vulnerable process. And think about that. So if there are pages that used that randomized base address that somehow might be specific to a specific vulnerable process, the attacker can now construct these pages and then infer that page exists. And by linking that to a specific process and maybe even to an IP address and so forth, it might be possible that the attacker can then map that base address to that specific VM. But still, what will the attacker really get? I mean, in the end, it's just a base address. So what we assumed in the beginning is that the attacker can reliably, or he knows a vulnerability where he can reliably hijack the instruction pointer. And the attacker has, at the point of where the vulnerability triggers, some control over maybe some values in the register or over some data. And we also assume that for these particular vulnerabilities that are interesting to actually first perform a CAIN attack in the cloud, we assume that the server process doesn't have an info leak vulnerability. And for server systems or server processes, this somehow makes sense, right? Because it's much more difficult to find info leak in server processes than it is maybe in a process where in a browser, for example, where you can construct an info leak with an arbitrary write, for example, under certain circumstances. So still, do these vulnerabilities really exist? I mean, does the attacker really gain something? And we found, for example, that one. So this is a Frag article from 2012, where the author, Redpants, describes how he was able to get reliable control over the instruction pointer by exploiting MS11004. It's a heap buffer overflow vulnerability that can be triggered remotely in IIS. And what the author actually showed was, or said was, the vendor initially said that vulnerability is not exploitable at all. And the author showed that, well, with enough determination, he actually was able to turn that impossible to difficult. So it's not yet easy to exploit, because in the conclusion, what he actually got was he got control over the instruction pointer. But he says, well, there is still ASLR and data execution prevention that need to be subverted. And these are exactly the cases where CAIN can make the difference. So in a cloud environment or in a virtualized environment where the attacker has control over another VM, he can actually exploit these vulnerabilities then reliably, because he can break ASLR then that is required and perform the code reuse attack. So is it really an issue in real-world environments? Like Kaveh mentioned before, we contacted some cloud providers, and if KVM is used, it is actually very likely that KSM, so the memory deduplication, is enabled. And there was one cloud provider that actually disabled it, and this was not because of security, but because of performance issues. So that cloud provider's workload was so specific that KSM in the end introduced performance overhead. So that's why they disabled it, and not because of the side channel. So memory deduplication seems to be used in real cloud environments, at least for KVM. And the other thing is that most providers, if you look at infrastructure as a cloud services, you can still, as an attacker, rent different kind of VMs with different memory. So most of the offers actually offer more than 4 gigabytes of memory. So from an attacker point of view, an attacker could just rent one of these machines, and he would have enough memory to actually mount the attack. And the other interesting thing is now, if the attacker targets a specific VM, well, that's one case. But the other case is maybe the attacker is just interested in looking around and looking what is on that on the physical system. And most of the time you have a lot of VMs that run. So the probability are quite high that then he'll notice that there is one VM with a certain vulnerable process that he can then where he can then use CAIN to actually make that vulnerability then exploitable. So we also looked at which virtual machine monitor vendors are actually vulnerable. so you see the memory deduplication implementation, or at least how the vendor calls it in that column. We also have from cert.org that vulnerability note where they try to assess as well which of these vendors are actually affected. Here you have the column with what we actually think if they're affected or not. And the last column is actually if the memory deduplication is enabled by default or not. And what you see is if you use KVM like used in Ubuntu or Red Hat, KSM is enabled by default, and we verified that the attack works there. So these virtual machine monitors are affected. Then cert.org says that Parallels virtualization solution is affected by it as well. So we were not able to verify that. So I don't know what they really use in the end. Now in the Microsoft world, so if you look at Hyper-V, Hyper-V does not implement memory deduplication for memory pages. So naturally, Hyper-V is not affected by it. So there everything is fine. And Zen, apparently they're also not doing it, but I think we got an email from them stating that they were thinking about implementing this. So they probably take these results into consideration. And for Oracle's VirtualBox and VMware, so there is page-based memory deduplication there implemented. It's called Page Fusion in VirtualBox and TPS in the VMware world. So we think they're probably vulnerable if it's enabled. So in both of these cases, memory deduplication is not enabled by default. So with the default configuration, you're fine. Although VMware, I think, started to disabling it by default 1 or 2 years ago. So if you have maybe old deployments, they might still use memory deduplication. So we disclosed the issue, of course. And the question is, is there like a fix? And the problem, of course, is who should actually fix it? Because it's a little bit difficult. In the end, it's a feature from a virtual machine monitor vendor's point of view. So other vulnerabilities, typically there are maybe bugs, you can fix them, the software still runs, everything is fine, right? But in that case, it's like a feature that they advertise, right? So people use it maybe because of that feature, because cloud provider can save some memory. So it's very resource efficient. So it's of course not very apparent that it's not that easy to fix from a vendor's point of view because of that, because they advertise it as a feature. So we informed, of course, several virtual machine monitor vendors that we thought might be affected in the beginning of June. We got replies from actually everyone, but the overall perception from the VMM vendor's point of view is it's actually a low severity issue for them. They say, well, it's a feature, don't use it, right? If you think it's a problem, so you can just configure it and then it's fine. So in the end, it seems that it will not be fixed. And this is, to some extent, of course, we understand that. If you think that threat scenario might affect you, then just don't use it, right? But we propose certain mitigations as well. They were not very specific. Of course, the first big mitigation or the apparent mitigation would be just deactivate memory deduplication, if you think this might be a problem. But there might be other mitigations as well, right? So what we proposed, we didn't propose a very specific way to do that, but more the concept of detecting the attack when it's going on. So the virtual machine monitor should actually see a certain pattern in page faults and a certain memory allocation pattern. So it should be somehow possible to detect that in the virtual machine monitor itself. Another way to mitigate the issue would be to actually increase ASLR for code pages, or in general, just make ASLR stronger. And another way would be to make it possible, or making sure that these sensitive memory pages that might be used to leak this sensitive information, like the ASL base address, but maybe also to leak other information, that they just don't exist. So in the case of code pages with ASLR, there might be certain compile time techniques, or you could make sure that this first page just doesn't have only the image base field that introduces entropy, but maybe introduce some additional randomness in them, or so forth. But for the time being, unfortunately, this is the only thing you can really do. So if you think it's a problem, you should deactivate memory deduplication. So we're actually already through. So the take-home messages from this briefing from our point of view, should be the following ones. So memory deduplication is considered harmful. And there were some papers and also some attacks before, but this is like, in my opinion, a certain new dimension. So the attack is very reliable. It's not just working in an academic setting. And it somehow shakens one of the foundations of exploit mitigations, namely ASLR. So memory deduplication is for sure harmful and should be seen that way. It doesn't mean that you should not use it, but it depends on the scenario. We also presented a practical attack against it that is able to break ASLR for co-pages at least in co-located VMs. And maybe the final or the most important take-home message here is the last one. If you think that you cannot trust the VMs that run next to your VM, or if you are a cloud provider where you might think that this threat scenario might affect you or your customers, then don't use memory deduplication in your cloud. So that's it from us. So we have time for questions. Yes.
So I thought about an easy sound fix. So if you don't disclose the read time, the actual read time back to the client, but you add an additional caching layer, and you just report back a random time for every operation there is, right? It doesn't necessarily has to happen. It can still sit on the cache. And
okay, but how do you implement that? I mean, in the end, it's a hardware virtualization. So the attacker will just execute the instruction to read the cycles, right? You want to change the hardware to do that, or?
So it will return back from that private operation after so much time, right? But it's running on a virtual CPU. So it's up to the hypervisor to decide when that function is returning.
Yeah, but then you have to slow down all the other writes, right? Because essentially, so it's a page fault, right? That is a slow that we are detecting, right?
Okay.
So for you to mitigate it like that, you have to slow down all the other writes by a factor of 10 or something, which is not feasible.
And basically makes memory deduplication useless, because probably the time you are detecting is the time needed to remove the duplication from the write. So it's probably faster to just remove memory to the deduplication.
Yeah. Yeah, that's also our suggestion. I mean, there is no easy fix, essentially.
Did you try this against anything else but ASLR?
So we did go, and so one other thing that we need to leak to be able, so if you think about it, you want to attack a VM, right? You also need to know its IP address. So we also found out pages that had IP addresses uniquely. So then you can think of using the same CAIN attack to leak IP addresses from neighboring VMs. So then you have the IP address, you can scan for vulnerabilities, and then you have ASLR, which we can use to attack reliably.
And you can enumerate, for example, operating systems as well, right? So, I mean, there are a lot of unique pages. So, and if you do it in a clever way, you can just enumerate and find out what kind of operating systems run on the same physical hardware. I mean, this was shown by one of the first papers in 2011, I think, that was published in Eurosec, yeah. So that's why we didn't mention it, but of course, I mean, the attack then, I mean, you can use it for a lot of things in the end, right? As long as you find these interesting pages that might, and then you can brute force, if you have some entropy in there, you can just brute force.
So the proof of concept is quite modular. So it's just a matter of taking a page and telling where to look for entropy, and then you can essentially perform it on arbitrary pages. But you have to give the tool the page, essentially.
More questions?
Would it be possible to do asynchronous writing, that you return all that the hypervisor will always return the same writing time, because it will let asynchronously do the copy and write.
But then how would you ensure consistency of the memory subsystem? Because there might be immediately another instruction that tries to read that value. So all the locking primitives, for example, use this. So.
Well, it's still in the queue to be changed. You could check if when it reads from there, if the queue something that I'm not very familiar with.
This needs to be implemented then in hardware, right? So then the current commodity hardwares, because the writes the hypervisor doesn't see, right? This is completely like virtualized by hardware.
Can I disable it inside my virtual machine or just the provider?
Just a provider. I mean, I don't see. Maybe, I mean, if the provider gives you an administration interface, you can say, I would like to run on a physical system where there is no memory deduplication enabled. Yeah, but I mean, no, you cannot disable it because it's a virtual machine monitor that just does it. Yeah. And that's one of the problems, right? So even if you go to these cloud providers' websites, I mean, they will not. I mean, you will never see like when you buy it, you will never have like a feature. Yeah, we use memory deduplication, right? I mean, because it's actually for you as a customer, it's not a feature. It's just for them interesting, so they can put more virtual machines on the same hardware. So,
but you can detect it.
Question. Can I just modify my binaries with single bits that they don't get deduplicated? Because they only get deduplicated when they're really binary exactly the same, right?
Yeah, so if you if you change your DLLs, if you manage to do that in Windows to make your DLLs look differently, then yes, you can subvert the attack.
I can just change one string in the DLL and its binary seem not the same thing. Like
Yes.
the arrow is message string or the
Yeah.
DOS string thing in the beginning.
Yes, but then there are also other pages, right? So we didn't talk about data pages, right? Yes, so the data pages you cannot really do much, right? So,
yeah, and there might be also interesting pages in the kernel, right? So the thing is, I mean, we took that ASLR like a use case, right? Because it's interesting, it has some security implications, but the concept is much more universal in the sense of if you find interesting pages that might, if you can infer that they exist, might give you some value as an attacker, then it's possible. And we didn't look at all pages, right? So I mean, in our case, we were very lucky looking at the first page of every portable executable image. I mean, it was so funny. We just looked at it and it was, okay, here it is.
they made it for our attack to work.
Yeah, I mean, it really felt like someone was waiting for us to just find it. I mean, it was, yeah. And probably a more determined attacker has more time and more insights, right? I mean, we don't know what such an attacker can do, but... So I would not see the issue like, okay, let's just fix that particular issue, right? And let's just change the first page of a DLL, right? It's more like a conceptual issue that, well, you have to get all these opportunities and find them and fix them.
Other questions?
Okay, and then please also complete the speaker feedback survey. So we were told to put that as the last slide. So, so thanks for your attention.
Thank you.